For this lab, we built many different circuits and recorded data about those circuits to observe the applications and correctness of the loop and node rules. I used a circuit simulator for my circuits rather than real components, which had an effect on my results that I'll discuss more at the end of the video. In the first system, we have a circuit with two resistors in series, and you can see that the current is 0.02 amps, and this checks out since the voltage divided by the resistance, which in this case would be 3 divided by 147, equals 0.02. Next, we observe that reversing the ammeter's connection doesn't change the reading it gives. It still shows this 0.02 amps. And then we replace one of the ammeters with a voltmeter here. And you can see that the current is 0 and the voltage is -3, which makes sense since this is effectively the same thing as putting it across the battery like so. And then if we were to close this circuit and measure the potential difference for each part of the circuit, you'll see that it's 3 across the battery, it's -0.96 across the first resistor, and it's -2.04 across the second resistor. And if we think about it, according to our loop rule, the sum of the potential differences around the circuit should be 0. And if we add up 3 plus -0.96 plus -2.04, we find that it comes out to exactly 0, as you would expect. And here I have drawn an approximate graph of the potential versus position across the circuit, just around the circuit. You can see each position is labeled here. And when I connect the voltmeter across this 100 ohm resistor right here, we see that the ammeter doesn't change at all, no matter what I do with this here. And this, even though I am altering the circuit, but we saw earlier that the voltmeter here doesn't actually complete the circuit. It doesn't actually affect it. It's just measuring what the voltage is at each of those points. That's just how it works in the simulation. And if we were to replace this voltmeter here and we were to connect an ammeter instead, you'll see that the current changes to 0.06 because there's no resistance in the ammeters in the simulation. So instead of going through the resistor, the current is just going to go through the ammeter. And we can even calculate to check if this is what's happening or not, and you'll see that 3 divided by 47 equals exactly 0.06. So it just shows that it's only going through this first resistor. And in the end, this is a simulation rather than a real circuit, so we know for a fact that the resistances in these resistors are exactly 47 and 100 ohms, and while the resistances of the ammeter and wire are both 0, unlike in the real world where they would inherently have some resistance in them. In the second system, we have an RC circuit here with a 10 ohm light bulb and a capacitor in series. And when we run the circuit, we will see that the light starts off bright and then it dims out as the capacitor charges up. And when when it's just the capacitor connected, the current flows through the circuit to charge it, which turns on the light bulb until the capacitor fully charges. And when the battery is removed, the current flows again as the capacitor discharges and turns on the light bulb again. It took about 15.3 seconds for the capacitor to fully charge with the 10 ohm light bulb and 27.3 seconds with the 20 ohm light bulb. And in order to discharge, it took the capacitor 15.5 seconds with the 10 ohm bulb and 27.7 seconds with the 20 ohm bulb. And in this last system, you can see that we have a fully charged capacitor and it is connected to a 30 ohm light bulb. And if we play the circuit, we can see the voltage chart being made right here. And from this measured data, we can calculate the RC. All you have to do is use this data to plot the natural log of the measured voltage at a given time, divided by the initial voltage measured, and do -1 divided by the slope of that graph in order to get the RC. And for my data, I got RC equal to 6.001, which is extremely close to the expected RC value of 30 times 0.2, which equals 6. So we can say that this is fairly accurate. And now looking back, we have to consider what would have happened if I did this lab in real life and used an actual ammeter instead of the ideal simulated one that I used for the lab. And what I would have seen is that real ammeters have their own resistances, unlike the ones in the simulations that have 0 resistance because they're ideal. And obviously having resistance in the ammeters would change our values and potentially mess up some calculations. And another question we have to consider is what if we did this experiment in real life and we used a real battery to charge a real capacitor with no resistor? In our ideal model predicts that the capacitor would fully charge instantly, but this would not be the case in the real world since real batteries and wires have resistance of their own that would slow the process down. Another potential issue is that if we had the same battery being used throughout the experiment or for multiple experiments, real batteries drain and equipment wears down, so many of the values and timing could be off. Thank you for watching my lab.